To learn naming, you first need to focus on your hydrocarbons. Reminder, hydrocarbon means it's a molecule containing only carbon and hydrogen atoms. No oxygen, no nitrogen, no fluorine, no halogens in general, anything else. Just carbons and hydrogens. Hence the word hydro for hydrogen and carbon for carbon. These include your alkanes, alkenes, and alkynes, so your compounds that are singly bonded. Again, alkenes are double bonds and alkynes are triple bonds. And aliphatic hydrocarbons. Alkanes, again, saturated with hydrogens, meaning that every carbon in there is sp3 hybridized, tetrahedral in shape, has 4 single bonds, has free rotation around that bond. Alkenes are unsaturated, meaning that they do not have the maximum number of hydrogens we could have based on carbon. They contain double bonds. Either they can contain one single double bond or they can contain multiple double bonds. Polyunsaturated is when it has multiple double bonds. The carbon involved in the alkene itself, so the carbon that has that double bond in it, is sp2 hybridized, unless it has 2 double bonds attached to it, it's sp hybridized. Alkynes contain a triple bond. Again, at least 1 triple bond makes the compound an alkyne overall, and they are more reactive than alkenes. Alkenes are more reactive than alkanes. Again, the alkenes and alkynes have that restricted bond rotation. They cannot rotate around that multiple bond. So you do just have to memorize names of the different alkanes here. Straight chain alkanes, you guys are responsible for carbons 1 through 10. This will also help you when naming other functional groups though, okay? The beginning of the name becomes important on the other functional groups. If you have 1 carbon, it is methane. 2 carbons, ethane. 3, propane. 4, butane. 5, pentane. 6, hexane. 7, heptane. 8, octane. 9, nonane. And 10, decane. That's what you're responsible for in this class. And I will just tell you right now at the beginning of the name so it becomes important. So the meth, the eth, the prop, the bute, the pent, the hex, the hept, the oct, the non, and the dec become important for other functional groups as well when naming these compounds. You also need to recognize and be able to name common substituents, be able to name them from structure, or given their name, draw them. This all comes based on that parent chain, and we're going to spend some time talking about that in just a sec. But your parent chain is your longest carbon chain on here. And so this is my parent chain here, okay? For each one of these, this is my parent chain. What's off of it is your substituent. So if you have a single line off of it, that's called a methyl group. Again, 1 carbon is methane, 1 CH3 group off is called a methyl. If you have a CH2-CH3 attachment in a straight line like that, that's called an ethyl. If you have CH2, CH3, all in a straight line, it's called propyl. And if you have CH2, 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 CH3, all in a straight line, it's called butyl. You've got a few others over here that are a little bit different, but you do have to know them. First is your isopropyl. Notice this is still, it's a CH3, CH2, I apologize, the kitten is meowing right at the iPad right now. CH3, and so this line down here that I just drew, that's where it's attached into the parent chain. It's attaching at that middle carbon, and that's called isopropyl. Isobutyl is this group here, okay? So you've got a CH2 that's attaching to the main chain. That CH2 is attached to a CH, which has 2 CH3 groups off of it. Your sec-butyl, so it's adding 4 carbons plus their hydrogens to it. This is adding 3. 1, 2, that should be a C. 3 and 4. But it's how it's adding them is different. The sec-butyl has a CH3 CH2, CH2, CH3. But it's attaching at that second carbon, so second, and it's a butyl group. And then tert butyl looks like a shape of a T. It's got a carbon. Let's attach the parent chain with 3 CH3 groups attached to it. So overall 4 carbons. Again, this is 4 carbon, this is 4 carbon. And they all have the same number of hydrogens if you add it all up. But the way they're connected is different. Okay, we have also aromatic hydrocarbons that you guys are responsible for. Aromatic means it's a ring with aromaticity, meaning it has double and single bonds alternating to give resonance to the overall structure. Benzene ring is a structure with sp2 carbons. So this is a benzene ring. This is also the benzene ring. They're resonance structures. You're going to often see the benzene ring drawn like this. Don't draw that in Dr. Minter's class. He doesn't like that. Okay? But it's the kind of hybrid of the resonance structures. So often drawn with the carbon double bond, which is what's shown in these structures here. But note, it does not behave as an alkene. It is not an alkene. It is a double bond there, yes, but it's delocalized charge, delocalized pi bonds. That's why this structure is useful to see the delocalization. This shows it's spread across the entire area. That's the red is showing up here. The red is trying to show up here, and below is the delocalization of those pi bonds. So it's not that electron density trapped just between 2 carbon atoms. It's actually delocalized around that entire ring, and that's why the the chemistry is very unique for benzene rings. If the benzene ring is an attachment on a parent chain, we call it a phenyl group. So how do you name things? We're going to learn how to name alkanes, and we're going to expand to the other functional groups. Each compound name consists of 3 parts: the prefix, the parent chain, and the suffix. The prefix is used to specify position, number, and type of branches or substituents attached. It specifies position, number, and type of each functional group. The parent chain is your base. It specifies the number of carbons in the parent chain. You pick the longest carbon chain you have, or ring if a ring is involved with it. And the suffix, or the ending, specifies the type of hydrocarbon you have. So ane, ene, or ine for hydrocarbons, or the functional group if we're not dealing with an alkane, alkene, or alkyne. Not all functional groups have specific naming conventions, and there are priorities between the different functional groups that are followed if you have more than one functional group present in a molecule, and we will talk about that. You are also not responsible for all possible functional groups in this class. It is beyond the scope of this class to name all possible functional groups. So for alkanes, find the longest continuous chain of the carbon atoms. This is your parent or base chain. Functional groups determine the ending of the chain name. So alkanes end in the word ane. Groups that are branched off the main chain are called alkyl groups and are named as your substituents. Begin with the substituent closest to the end of a chain and count which carbon from the parent chain the substituent is bonded to. If 2 groups are equidistant apart, use the second branch to decide, and I'll show you what I mean by that in examples in just a minute. Substituent number, substituent name, base name, suffix. Functional group specification is how the names are put back together. You list the branches on the compound alphabetically. Letters like N and T and writing the word sec, so like sec-butyl, do not contribute to the alphabeticity here. You go by the main, so like 5-sec-butyl, I go by the butyl as the name. But the word iso, or the prefix iso, does count towards alphabeticity. Use the prefix if more than one of the same group is present. So if I have 2 of something, I say di. If I have 3, I say tri. 4 tetra, 5 penta, 6 hexa. Do not count the prefix, though, when alphabetizing these. If you have a cyclic compound, add the word cyclo to the parent chain name. Some other substituents you may see besides the methyl, ethyl, propyl groups. You can have halogens. We call these fluoryl, chloral, bromo, and iodo when they are the attachments. We can have a CN. Remember, this is a triple bonded compound. So if that is attached to something, we call it cyano. If we have an NO2 attached, we call it nitro. If we have an OH attached and it's not an alcohol group, if it's being named as a substituent, sorry, that word is hard tonight, with a different function group that's not an alcohol, we call it a hydroxyl group. If we have an NH2, we call it an amino group. For alkenes and alkynes, you need to find the longest continuous carbon chain that contains that double or triple bond. That double or triple bond has to be in the parent chain. Identify the branches of substituents. Number the chain so that the end is the end closest to the double bond has the lowest number assigned to it. Name the branches and substituents alphabetically and number the first carbon of the double or triple bond. So we can see in the structure here, we have a lot of carbons that we could start with, but we have a double bond right here. I have to keep this double bond in the structure, or in the parent chain. So if I could have counted 1, 2, 3, that includes it, 4, 5. I could have said 4, 5. Or I could say 4, 5, 6. That's what I'm going to do because it gives me the most carbons in my parent chain. Now this is a substituent group and this is a substituent group. But notice I started counting the carbon 1 right here because that allowed me to make this carbon 2. If I had started counting the other direction, 1, 2, 3, 4, 5, 6, now my double bond doesn't show up until carbon 4 instead of carbon 2. Counting it this way, I'm able to make it at carbon 2. So if I have the name and I want to go to a formula, draw number base chain carbon skeleton. So if I'm looking at this, and again, I will show you examples of these and I'll make the additional practice video. But when I've got hexane, ane tells me single bonds. Hex tells me 6 carbon. 1, 2, 3, 4, 5, 6. Now, I'm just going to, because I'm drawing it myself, I can do what I want. I'm going to put the carbons this direction. I'm told that the second carbon, I have a methyl group. I know methyl is CH3. I'm told that the fourth carbon, I have an ethyl group. I know ethyl is C2 or CH2CH3. There's my group. It's the same as these, it's just drawn in the skeletal structure. Let's work on naming these compounds here. Okay, let's zoom in on this one. Well, first off, I see that I have a triple bond right here. So that means I need to incorporate that into my parent chain. 1, 2, 3, 4, 5, 6, 7. Okay, that's one possibility. I don't know what the right answer is yet. 6, 7. Okay. And truthfully, that doesn't matter. If I made that 6, 7, this is still a methyl group at the 6. If I make that 7, it's still a methyl group at the 6, so it didn't matter. Let's see. 4, 5, 6. Nope, not the longest. 4, 5, 6. Nope, not the longest. So this is my longest parent chain. I know I have 7 carbons. So I know I have hept. I know I have a triple bond. So I have an Y-N-E ending. Okay? I know that I have a methyl group here because I learned my substituents' names. And I know I have an isopropyl group here because I know my substituents' names. And isopropyl looks like the Y shape where it's attached to the long chain here. Now I have to put it together and I have to tell where everything is. My triple bond is at the second carbon. So I'm going to tell us that the ine is at the second carbon here. My methyl group's at the 6th carbon. My isopropyl group is at the 4th carbon. Alphabetically, iso comes before methyl because iso does matter alphabetically. So I'm going to say 4-iso, propyl. And notice I'm putting a dash between numbers and names. 6-methyl. So every time I switch between a number and a name, I'm putting a dash in. And then I have hept 2-ine. I'm emphasizing that the triple bond is at the second carbon. So 4-isopropyl, 6-methyl-hept-2-ine. Let's look at this one here. I've got the double bond I got to pay attention to. So 1, 2, 3, 4. Probably not. 4, 5. Okay, that's possible. Let's see. 1, 2, 3, 4. That's not possible. I didn't keep the double bond in there. Let's try over here. 1, 2, 3, 4, 5, 6. That's definitely longer. Now, do I want to count from that direction? This gives me the double bond at the third carbon. If I went the other direction, 1, 2, 3, 4, 5, 6. Okay, that doesn't make a difference. So how do I decide which way to go, the pink or the blue? Either way, my double bond carbon is going to be at the third carbon. I'm going to look at my attachments. It's going to have my methyl group at the third carbon if it's blue, and then fourth, and third carbon and then fourth if it's pink. The compound is literally symmetrical, so it does not make a bit of difference which way I'm going to draw this one. So I'm just going to do it this way. 1 through 6. I have 6 carbon, which I know is hex. I know my ending is ene, because I have a double bond, and I know that my ene is at the third carbon. I see here I've got 2 methyl groups, one at the third carbon and one at the fourth carbon. So what I'm going to call this is 3, 4, emphasizing the 2 different positions of it, dimethyl, emphasizing I have 2 of them, hex, 3-ene. Hex for 6 carbons, my parent chain, 3 for telling me where the double bond is, and ene to tell me it is the double bond that I'm specifying. Let's look at this one. 1, 2, 3, 4, 5, 6. 5, 6. 5, 6, 7. Okay, so that's not it. 5, 6, 7. Okay. I could go either way. Which way am I going to actually start numbering? It can matter too. I was going to say something first. If I number it this way, my first group shows up at the fourth carbon, okay? If I number it starting on the other end of my chain, 1, 2, 3, 4, 5, 6, 7, my first one is at the third carbon. That's better. I want it the third carbon. If I did 1, 2, 3, 4, 5, 6, 7, same thing, it's at the third carbon. If I did like this, my third carbon has an ethyl group. If I did the 1 and 2 down here, my third carbon still has an ethyl group, so that doesn't make a difference. So I'm going to leave it like this. Okay, so I've got 7, which I know is hept. I have all single bonds here, so I know it's just heptane. I don't have to emphasize any double or triple bonds. I can see at my third carbon, I have this ethyl group. And at my fourth carbon, I have this isopropyl group. Ethyl comes before isopropyl in the alphabet. So 3-ethyl, 4-isopropyl, heptane. Okay, now this one, draw the structural formula for 4-isopropyl 2-methylheptane. Okay, first thing I do is I look at the end of the name. And I see hept, and I'm like, cool, 7 carbon. And I see ane, and I say, oh, great, I don't have any double bonds. Triple bonds, nothing. So I'm going to draw the 7 chain. 7 carbon chain. 1, 2, 3, 4, 5, 6, 7. Cool. I'm just going to say that the carbon one is down here because I can, because I'm drawing this how I want. It tells me at the fourth carbon, I have an isopropyl group. And I know isopropyl looks like that Y. It tells me at the second carbon, I have a methyl group. And that's it. I drew my compound. Their naming does get more complex, of course, we have functional groups and such. But first, let's talk about some monosubstituted benzene derivatives. Again, benzene is that hexagonal ring with the alternating double and single bonds. So to name these, you name the substituent attached, and then you can just say benzene after it. So you can see here, like the fluorine on the benzene group, we just call it fluorobenzene. The propyl on the benzene group, we just call it propylbenzene. Okay, if it's just the main group, that benzene group is only attached, we name the attachment and then just say benzene. Some common names, you do have to know these. You're going to see these in organic chemistry, so might as well start learning them now. If we have a methyl group attached to the benzene ring, we don't call it methylbenzene, we call it toluene. If we have that amino group attached to the benzene ring, we don't call it an aminobenzene, we call it aniline. If we have that OH group, we don't say hydroxybenzene, we call it phenol. And if we have this structure, this attached to the benzene ring, this double bond, this carbon double bonded to itself with the hydrogens attached to it, we call this styrene. You do need to know these common names. You will see this in class. So toluene, aniline, phenol, and styrene, you do need to recognize these groups. Disubstituted benzene derivatives. Number the ring starting at the first substituent and then move towards the second. How do you know what the first one is? Alphabet. Order the substituents alphabetically. So 1, 2, 3, 4, 5, 6. How did I decide bromine was number 1? Because it's the first in the alphabet. So I decided to make it number 1. How did I decide to count counterclockwise? Because I need fluorine to have the lowest possible number compared to the bromine. So I've got 3 fluoro, bromobenzene. I'm giving up. That's getting messy. If you get 2 of the same, just call it di. I'm not going to call this methyltoluene. I'm just going to call it 1,2 dimethylbenzene. If you do have disubstituted benzene derivatives, they do have positions. You need to know these positions. They're called ortho, meta, and para, or OM and P. I call it ortho, meta, para. The 1 and 2 positions are called ortho. The 1 and 3 position is meta. The 1 and 4 is para. So if this is your carbon 1, notice ortho is literally at the 1 and 2 carbon. They're next to each other. That also means that even though it's not emphasized this way, this group right here is also ortho. Okay? Meta is the 1 and 3 position. So 1, 2, 3. It could also be here. This is also the meta position because I could count the other direction. And then para is the 1 and 4 position. So notice the names down here, like 2-chlorotoluene versus orthochlorotoluene, 3-chlorotoluene versus metachlorotoluene, 4-chlorotoluene versus parachlorotoluene. You have to recognize ortho, meta, para. It is very important when you get into organic because you're going to different reactions are what we call ortho-para directors or meta-directors, meaning it will actually cause things to go to the ring in certain positions based on the electronics of the structure and the chemistry behind it. So you have to recognize ortho, meta, para. Again, ortho means next door to each other, meta means there's one position away from each other, and para means they're completely opposite to each other on the ring. So again, if I was to name these, if I start 1, 2, 3, 4, 5, 6, I've got the, I can call this 1,4, I could call this 4-chlorofluorobenzene, or I could say para. For this one, 1, 2, 3, 4, 5, 6, that is the meta position. So meta dibromobenzene, okay, instead of 1, 3 dibromobenzene. And then you have your other functional groups, and you are responsible for naming these things. And this just comes from practice. Alcohols, the main chain contains that OH group. So you can see here, like the OH group is on that main chain. You number the main chain from the ending closest to the OH group. So on this one, 1, 2, 3, 4. That's 5, 6, 7, 8. Okay. Give the base name OL ending. Prefix is carbon number where the OH is attached. Name is a hydroxy group if there's other higher precedence group present, such as an aldehyde, ketone, or carboxylic acid. So if I have more than one functional group attached, I do name it with a priority for the other functional group, and then I name that OH group as hydroxy. Ketones and aldehydes. Ketones just end in the systematic naming "one". So for example, 2-pentanone, we see the word "one" there. Penta meaning 5, so 1, 2, 3, 4, 5, and 2 telling me where the ketone group is. Remember, ketone is a carbon double bond to an oxygen, so that 2 is telling me it's at that position. Aldehydes, the systematic naming ends in AL. So for example, 2-methylbutanol. Common names end in aldehyde. You're going to see that written as well. So like ethanol versus acetaldehyde. The 2-methylbutanol, butanol means 4. But remember that aldehydes have to be the first carbon of an aldehyde. So the carbon that is double bonded to the oxygen is always your carbon 1 in an aldehyde. No exceptions to that. Ketone, we have to specify where it is because remember, ketone has carbons on either side of that carbonyl carbon. But an aldehyde, this is always carbon 1. No exceptions to that. Okay? Ketones, we have to specify. But aldehyde, the carbonyl carbon is your carbon 1. So the carbonyl functionality is always located on carbon 1, is therefore never named. You must specify the location of it for any ketone, though. 2-methylbutanol, so 1 and then 2 would have a methyl group right there. Ethers, again, formula ROR, where the R's could be the same or could be different. You could have R prime here. You're going to just use the word ether at the end. So you're going to name the two sides of it and then call it an ether. So like diethyl ether. I've got 2 ethyl groups attached, and it's an ether. Okay? Just looks like this. Name each alkyl group attached to the oxygen, and then add the word ether to the end. Carboxylic acids do get the highest precedence. So if you have a carboxylic acid with other functional groups, you're going to take the carboxylic acid as the name of the compound, as the base name. So carbon of group, the carbonyl carbon is always carbon 1. So this is carbon 1, this is carbon 2, carbon 1, carbon 2, carbon 3, carbon 4. It's always the base carbon. Position would not be indicated because it has to be at the end because I have to have that carbonyl carbon attached to an OH group to be a carboxylic acid. And then I changed the ending of the name to oic acid. So ethanoic acid, also known as acetic acid, butanoic acid, okay? Esters, again, esters have that ROC double bonded to an OR group, or you can draw it the other direction as well. Like down here, what I mean by that is like, put it like this instead. Either one is fine. But that's an ester group. Esters are made by reacting carboxylic acids with an alcohol. So because of that, they actually are named based on the original groups that came together to make it. We take a carboxylic acid and alcohol, and we kick off water. We do that, though, by kicking off the OH group off of the carboxylic acid and the hydrogen off of the alcohol to make the water and the new ester. So the ester itself is made from the carbonyl carbon over came from the original carboxylic acid, and the oxygen remaining, and then the R group off of the side of the oxygen, the singly bonded oxygen, that came from the original alcohol. So you name the alkyl group from the alcohol first, then the acid name with the O8 ending, which I know can be confusing at best. But if I look here, this is from the carboxylic acid, this is from the alcohol, okay? So you're going to name the oxygen that is singly bonded first, because that comes from the alcohol. You don't name the oxygen, though. We know the oxygen is there because it's an ester. We're going to see that in the O8 names. We're going to name this first. CH3 group is a methyl group. Then we're going to name the rest of the compound. 1, 2, 3, 4. I know is butyl. I know but for 4. So butan And then we read the O8 to emphasize that it is in fact an ester. Again, you can see some of the esters here. Methylpropanoate, the methyl group, and then the rest of the compound due to the carboxylic acid. Prop means 3, so propan. You'll see just from the way the name sounds, we often leave a little bit more of the name on there. We wouldn't say propoate. It sounds weird, but propanoate sounds better. But we've got the 3 carbons, so the propanoate there. Let's see. We've got, from the alcohol group here, we've got an ethyl group, so we've got ethyl. And then we've got 1, 2, 3, 4, 5, which is pent, so pentanoate. Amines. Amines are just nitrogen-containing compounds. They smell pretty bad. You're going to name the alkyl groups attached to the nitrogen itself and then add the word amine to the end of it. So you can see here I've got a methyl group attached to a nitrogen. It's called methylamine. Here I've got 2 methyl groups attached. I call them dimethylamine. Here I've got a methyl group and a propyl group attached, so I call it methylpropylamine. More complex naming will come in future classes. Remember that your amines are weak bases, so these can be involved in some of the chemistry that we do. An amine is an ammonia derivative where 1, 2, or 3 of the hydrogen atoms are replaced by hydrocarbon groups. We are only naming simple alkanes in this class, okay? But you can see here like ethylamine. You can see dimethyl, meaning 2 methyl groups, amine. Ethylamine, you've got an ethyl group attached to it. Note that amines do have primary, secondary, and tertiary. Alcohols do this as well. Primary means that the nitrogen is only attached to 1 carbon atom and then the remainder are hydrogens. Secondary means that the nitrogen is attached to 2 carbon atoms. The rest is hydrogen. The remaining space is hydrogen because remember nitrogen wants to have 1 lone pair on it. A tertiary amine means that it's only attached to carbon atoms, no hydrogens present at all. And quaternary ammonium is when nitrogen has 4 bonds to it that are not hydrogen. So again, this can only be ammonium because it's going to be a positively charged species at that point. If I have tertiary, that means no hydrogens. Secondary means 1 hydrogen. Primary means 2 hydrogens. And then ammonia is just ammonia. But it's called primary because it's only attached to 1 carbon. So primary, 1. Secondary, 2 carbons. Tertiary, 3 carbons. Your ammonium cations, you guys should be comfortable with this. Thing came from the acid-base unit. I'm not going to go back through these, but you should be comfortable with it. Like if I have ethylamine and I protonate it, I form ethyl ammonium ion. If I have dimethylamine and I protonate it, I form dimethyl ammonium ion. You guys should be comfortable with those things. And Dr. Bonchamp made a diagram to help really kind of show this idea of primary, secondary, tertiary, and different compounds you can have. I did state that alcohols can also be primary, secondary, tertiary, and you guys are responsible for that. So let's go ahead and draw what that means. Let's say I've got a chain and I've got an OH on the end. This oxygen here is only bonded to a carbon that is bonded to 1 other carbon atom. That is called primary. So I take the OH group and I look at that carbon atom and say, how many other carbon atoms are you attached to? And if it is only 1 other, it becomes primary. This is secondary. This OH group is bonded to this carbon. This carbon is bonded to 2 other carbon atoms. Hence, that oxygen is a secondary carbon. And this is a tertiary. Tertiary. A tertiary alcohol. I look at the carbon that this OH group is attached to. And this carbon group that it's attached to is attached to 1, 2, 3 other carbon atoms. So it is a tertiary alcohol. We care about that because the chemistry is different for primary, secondary, and tertiary. And you guys need to know that. So you can see here, primary alcohol, a secondary carbon. It's attached to 2 different things. A tertiary carbon, meaning not hydrogen. Tertiary is attached to 3 things besides hydrogen. Quaternary carbons attached to 4 things that are not hydrogen. A tertiary bromide, this bromine is attached to a carbon atom that is attached to 3 other carbon atoms. Tertiary carbon, secondary chloride, primary carbon. You can see that the methyl group is primary carbon. That carbon's only attached to one other thing besides hydrogen. Secondary amine, it's got 2 things attached that are not hydrogen. It's only 1 hydrogen attached. I think that's basically all of them. But yeah, you guys can kind of see how we name the different things on here. And then just a couple examples. So what is the systematic name for the following compound? Well, let's see. I've got a functional group here. This is an aldehyde. I recognize it because I can see that carbonyl carbon with the hydrogen on the end, but that also means that has to be the first carbon. 1, 2, 3, 4, 5, and 6. So I've got 6 carbon, which I know is hex. Aldehydes end in the word al, so hex and al is what I'm going to call it. But I've got this group attached to it at carbon 4. It's a benzene ring, but when benzene is a substituent, we call it a phenyl. So I'm going to say 4-phenyl hexanal. See, number 2, what is the chemical formula of ethanoic acid? So ethanoic means 2 carbon. Here. Oic acid means carboxylic acid. So I got my carboxylic acid, I got my second carbon, that's all the carbons I need. And there's my formula. CH3, COOH, it's the same thing as acetic acid. Draw the Lewis structure for 1,2-butadiene. The ene is telling me I have a double bond. The di is telling me I have 2 double bonds. And the 1 and 2 is telling me where those double bonds are. The but is telling me I have 4 carbons overall. So let's just draw the 4 carbons first, okay? Now, I know that at the first and second position, I have a double bond. Now give all of your carbons enough hydrogens to give them a 0 formal charge. I don't think I could fit this. Nope, I'm going to leave that where that was. What type of amine is NN-dimethyl-3-pentamine? Don't worry about the NN yet. You guys learned that in organic. I don't care about that here. It's not the focus of this class. But is this primary, secondary, or tertiary, or quaternary? Primary means it's only attached to 1 carbon atom. Secondary means it's attached to 2 carbon atoms. Tertiary means it's attached to 3 carbon atoms. And quaternary means it's attached to 4. So let's look. I got 1, 2, 3. Tertiary. And the last example in this unit, the artificial banana scent is caused by the molecule shown below. What is the IUPAC name of this molecule? So I can recognize this as an ester. Okay, I recognize it's an ester because I have that carbonyl carbon, the oxygen, the chains on either side. It's definitely an ester. I know esters are named by finding the alcohol group first and naming that, and then finding the carboxylic acid group second. The alcohol group includes the singly bonded oxygen and everything past it. The carboxylic acid group includes the carbonyl carbon and anything to the other side of that. So when I look at this first one, the alcohol group, I've got 1, 2, 3, 4, 5. That is pent. And I'm going to name it as a substituent, which means it's pentyl. But that also means I got rid of A, B, and C, which is kind of cool. Now I look at the other portion. So again, 1 oxygen goes to each side, right? The one that's double bonded came from the carboxylic acid, and that's the one that's going to get the O8 ending. I have 2 of them here. I know 2 is F, so ethan, O8. I've got pentyl, ethanoate.